Problem number 6. A ball rolls without slipping down a ramp, which turns horizontal at the bottom. At the bottom of the ramp, the ball falls through the air, as in the diagram. If the ball starts from the position marked O, it lands 10 centimeters away from the bottom of the ramp. Which starting position will get the ball to land closest to 25 centimeters away? Solution for problem 6. The kinetic energy of the ball at the bottom of the slide is proportional to the height dropped down the slide, so the horizontal velocity is proportional to the square root of the height drop. The time to fall is constant, so we need the velocity to scale up by 2.5, which means the height drop has to scale up by 6.25. This is choice A. That was solution for problem 6. Problem number 7. A mechanism consists of 3-point masses, each of mass m, connected by two massless rods of length L and a torsion spring acting as a hinge. The potential energy of the torsion spring is given by Us. This system is designed to walk down a set of stairs, as shown in the figure. The angles θ1 and θ2, see figure, represent the orientation of the rods, and their rates of change, ω1 and ω2, are the corresponding angular velocities. Assume that the mass on the surface is instantaneously at rest, which equation correctly describes the total energy of the system. Solution for problem number 7. Using expressions for velocities and positions, we set up the energy as a sum of kinetic energy, gravitational potential energy, and torsional potential energy terms. Velocities in x and y directions we may represent in expressions 1 and 2, so the total energy E will be expression 3. After calculations we have expression 4, which is answer C. That was solution for problem number 7. Problem number 8. A symmetric spinning top, rotating clockwise at an angular frequency omega, is placed upright in the center of a frictionless circular plate. The plate then begins to rotate counterclockwise at a constant angular velocity omega. Assume the top's axis remains perfectly vertical and stable without any precession. From the perspective of an observer rotating with the plate, how does the top appear to rotate? Solution for problem number 8. When the plate begins to rotate, it does not exert any torque on the spinning top as the plate is frictionless, thus there are no external forces acting on the top that could change its angular momentum. As a result, the top's angular velocity in the lab frame remains unchanged. From the perspective of an observer who is rotating along with the plate at angular velocity omega, the apparent angular velocity of the top is given by the transformation omega top rotating equals omega top inertial minus omega plate. Plugging in the frequencies we have omega top rotating equals negative omega minus omega, which negative 2 omega. Since the negative sign indicates clockwise rotation, the observer on the rotating plate perceives the top to be spinning in the clockwise direction at twice its original frequency. This is the choice C. And that was solution for problem 8. Problem number 9. N circles in a plane, CI each rotate with frequency omega relative to an inertial frame. The center of C1 is fixed in the inertial frame, and the center of CI is fixed on CI-1, for I equal 2, etc. till n, as shown in the figure. Each circle has radius Ri equals lambda Ri-1, where 0 less than lambda less than 1. A mass is fixed on Cn. The position of the mass, relative to the center of C1 is R as function of t. For the n equals 4 case shown, which of the following statements is true? During the time interval from 0 to 2 pi over omega, the magnitude of acceleration of mass on C4 is 1 of 5. Solution for problem number 9. The orbit angular velocity and the rotation velocity are the same, which means it will always have the same phase, similar to Moon and Earth, where the moon always faces the same way relative to Earth. Therefore, the entire structure actually rotates as a rigid body, and the mass is simply moving in a circle, at constant speed. This is the answer E and what was solution for problem 9. The following information applies to problems 10 and 11. When two objects of very different masses collide, it is difficult to transfer a substantial fraction of the energy of one to the other. Consider two objects, of mass small m and big M much greater than small m. Problem 10. If the lighter object is initially at rest, and the heavier object collides elastically with it, what is the approximate maximum fraction of the heavier object's kinetic energy that could be transferred to the lighter object? Solution for problem number 10. Let the heavier object have initial speed v. It means that its kinetic energy E0 equal 1/2 of big M v square. In such an elastic collision, the final speed of the light object is approximately 2v, so its kinetic energy E is 1/2 small m 2v square. Thus maximum fraction E over E0 is approximately 4 small m over big M. Which is answer C. That was solution for problem 10. Problem 11. Now suppose that instead, the heavier object is initially at rest, and the lighter object collides elastically with it. What is the approximate maximum fraction of the lighter object's kinetic energy that could be transferred to the heavier object? Solution for problem number 11. Let the lighter object have initial speed v. So the total kinetic energy E0 of this object is 1/2 small m v square. Since big M much greater than small m, its final speed is also approximately v, but the direction of the velocity is reversed, so the impulse given to the heavier object is about 2 small mv. Then the kinetic energy E of the heavier object is p square over 2 big M, which is approximately 2 small m square v square over big M. Thus maximum fraction E over E0 is approximately 4 small m over big M. Which is answer C. That was solution for problem 11.